Welcome to our first set of notes. So the way these videos work is you're going to want to copy everything you see and everything I type on this page. So in order to do that, you're going to want to go ahead and take out a notebook. I would go in and call this, just so you could keep track, you're in Unit 5 and it is Lesson 1. I'm in the name of the lesson, Simplifying Radicals. Anything I open in a brand new page like this, you don't have to copy. It's just what I'll use to explain things and talk through things. It's like just an extra page for me. So I'm going here because before I start every lesson, I'm going to start with the CLO. CLO stands for Content, Language, Objective. Content means the stuff we're learning, like what's the actual math we're learning. Language is what's the language in the lesson that we care about. And objective just means goal. So really, this is just the goal of our lesson, the goal of everything I want you to learn. So for this lesson, the content language objective is students will be able to create in writing equivalent forms of expressions using simplifying radicals and the following language. If-then statements, simplify, radical, root, and exponent. So based on reading this, what do you think we're going to do today? So basically, to tear these apart quickly, the places you want to look is after the students will be able to. The word create tells you what you're doing. It's like your verb. Then in writing is just the fact that we do it in writing, because most math is done on paper, writing it out. And what are we creating? We are creating equivalent forms of expressions. So the word equivalent means the same. A form is just another thing. Like if this is in one form, we're creating something that's the same, but it's going to be different, a different type. And it's going to look slightly different, but it's still going to be the same thing. An expression just means math. Anything with numbers and letters without an equal sign is an expression. When you add the equal sign, it becomes an equation. And so, because the equal sign is equation, expression just means like any other math without an equal sign. So we're taking math that doesn't have equal signs in it and we're rewriting it. It basically means we're rewriting it in a new way. And how are we going to be rewriting it? We're going to be rewriting it by simplifying radicals, which is why it says using simplifying radicals. So that's the specific math we're going to use to make these equivalent expressions, to make these things that are the same thing, but they just look different. So this is the process we're going to use. And then this is the language we're going to use to do it. So if-then statements is the way we're going to talk about it. I'm going to explain that in the notes. Then the next 4 words are just our vocabulary. Our vocabulary words are simplify, radical, root, and exponents. And we're going to go through all of those in the notes. So to start the notes, we're going to always start with the vocabulary words. So the word simplify means to combine things that will allow you to make the expression smaller. Simplify usually means you put 2 things together in some way and it becomes smaller numbers, or if it's really long, it becomes shorter. The word exponents means a little number in the upper right-hand corner that tells you how many times to multiply a number to itself. So, for example, I'm going to jump down here to examples just so you can see it. When you see 2 in a parentheses with this little 2 up here, that's an exponent. So this 2 has an exponent of 2. That's one way to read this, 2 with an exponent of 2. They might also say, here, I'll write this down in the don't copy space just so that you can see it. Insert equation. So there's a few ways I can read this aloud. I can say 2 with an exponent of 2. I could also say 2 to the degree of 2. That's another way to say the same thing. And then the common one is 2 squared. Because when the exponent's 2, we often say the word squared. However, let's say this wasn't a 2, let's say it was a 5. Then I don't have a special word for that. So this wouldn't work. I would either have to say 2 with an exponent of 5 or 2 to the degree of 5. Oh, and I just remembered the third one. It's 2 to the power of 5. So when it was a squared, I could have also said 2 to the power of 2. So there's 3 ways to say any of them. You can say with an exponent of, to the degree of, or to the power of. And it all means the same thing. But there's a couple really special ones. So one of the special ones you know is anything to the power of 2. I told you we can also say it's squared. So 2 squared. If it was a different number, let's not use 2. Let's use 7. Now it's 7 squared. So to the power of 2 is a special one that has the name of squared. The other one that's special is if it's to the power of 3. I don't know why they deleted. With the 2 up there, it's 2 squared, or 7 squared. Wow. With the 2 up there, it's 7 squared. When it's a 3 in the exponent, we can read it as 7 cubed. So when it's to the power of 3, it has a special name as well called cubed. Other than those 2, the rest of them will either say one of these 3 things, any one that people like to say. All right, back to the notes. All right, so, oh yeah, quickly, it tells you how many times to multiply that number to itself. So in this case, when it says what's 2 to the power of 2, it means you're going to take 2 and you're going to times it by itself. And 2 times 2, and we're going to do it twice because there's a little 2 up there. And 2 times 2 is 4. So the answer to 2 squared is 4. So the next vocabulary word is radical. A radical is any expression with a root in it. So any strain of numbers and letters, if you have a little root in it, then it's called a radical. So what I mean by root is the little house. That's what I've heard a lot of people call it. It kind of looks like this. Like it has that little house there, but there's multiple types. So there's this one here. Oh, back to our notes that you don't have to copy, but you just need to understand. So let's talk about roots real fast. When it's this type of root, it means it's called a square root. But it is not the only type of root. It's called a square root because we pretend there's a little invisible 2 right up there. So these mean the same thing. We just don't write this 2 here because the square root is the most common one that shows up in real life. And things that show up in the real world a lot, they have special names. So squared shows up a lot, and so does square roots. And so because it shows up so much, they're like, okay, if there's no number right here, we're going to assume it's a square root. and it has a little 2 there, and it's like this invisible little 2. However, it's not the only type of root that exists. This one also has a special name, and it's called a cubed root. So just like if to the power of 3 is called cubed, when it's in a little house like this and it has a little 3 up there, it's called a cubed root. And then if it has a little 4 up in there, it's called a fourth root. And from there, it's just using the TH. So if it's a 5, it's a fifth root. And it's a 6 if it's a sixth root. If it's a 7, the seventh root. And that's how we call the rest of them. So back to the notes to explain what they mean. So it's the little house, and they are the inverses to exponents. All right, I use more big words. Inverse means undo. For example, back to don't have to copy this part. If I have $5 and I add $6, now I'm at 11. If I want to undo adding 6 to go back to 5, my original amount, the inverse of adding is subtracting. Then if I minus 6, I go back to 5. So adding undoes subtracting. So for example, when we solve for x, if I had x minus 5 equals 9, basically it's saying what minus 5 is 9. Well, if I want to undo this minus 5, I can draw my line, and the inverse of subtracting, remember we just said is adding, because adding and subtracting are inverses. So if I add 5 to both sides, because what you do to one side, you always have to do to the other. On this side, they cancel because they're inverses. They undo each other. They eliminate each other. They cancel each other. All those words mean the same thing. Cancel, eliminate, undo, inverse. They all just mean it gets rid of. And now we're left with x on the left side. This canceled, and it's going to equal 9 plus 5, which is 14. If you are struggling with adding, you might want to do the warm-up on adding positive whole numbers in the skill building place. Remember, you have to do 5 of those folders in order to pass the class, any 5 you want. So if adding positive numbers is a struggle for you, you should go work on that. All right, so adding and subtracting are inverses. So is multiplying and dividing. Multiplying and dividing undoes each other. So if you're dividing something to undo it, you multiply by the same thing. Same if you're multiplying to undo it, you would divide by the same thing. So exponents and roots are inverses of each other, which means if I were to take 5 and square it, that means 5 times 5. And 5 times 5 is 25. So then if I have to do something to this 25, because I want to turn it back into this original 5 that I had before I squared it. So to undo the fact that I squared it, what I do is I take the square root of 25. Because the square root of 25 actually means what number, when squared, is 25. And the answer to that question is 5. So we have calculators that take square roots for us. If you go to my class and we go into the class, and you scroll down, there's this section that says Math Tools. And when you click on that folder, at the very top, the very first one is an online calculator. It's a great calculator. When you click on it, it's going to go to Desmos. It'll let you graph, and I'll teach you the graphing function when you need it. But for now, you can do square root of 5 in 2 ways. You can type SQRT, but once I type the T, it's going to change it into the square root. See that? Square root of 25 is, and the answer is down here in this little right-hand corner. You see the equals 5 right here. My mouse is moving around it. All right. So that's one way that we can use this calculator to calculate things. So this is a square root. Another way, if you don't want to type SQRT, you can also down here in this little bottom left corner, it has this little keyboard. If you click up, a bunch of math will pop up now. And the square root function is not showing, so I think I have to hit this word that says functions. All right, so I have to hit functions, and I had to go all the way over to miscellaneous, but right here now you see the little square root sign. So if I'm going to delete this one away, and then now if I hit this, so it first goes up here, like let's say I want to do a cubed root, so I could type it in there, like a little 3 right up there. And then the number that I'm taking the cube root of goes under the little house line. So then let's talk quickly about cubed roots. So cube roots undo are the inverse to when we cube something. So if I take 5 to the power of 3, it means 5 times 5 times 5. 5 times 5 times 5 is 125. Now, if you didn't know that in Desmos, I could have done 5 to the power of, and I go up there by hitting Shift 6. And so Shift 6 gives me an exponent to the power of 3 is, look, 125. So is if I did 5 times 5 times 5. That is also 125 because they're the same thing. Which means, what's the cubed root of 125? Oh, look, the answer is 5, because what cube root does, the cubed root of 125 asks itself, what number, when cubed, is 125? So that means what number times itself 3 times, because cubed means times itself 3 times is 125. Well, we just know that from before that the answer was 5, because 5 times 5 times 5 was 125. So in the same way, to the power of 4 and the fourth root are inverses, they'll undo each other. Yeah, and so that is what a root is. So let's work through each little example. I already talked about how 2 to the power of 2 is 4, because 2 times 2 is 4. But what about for negative 2? Negative 2 times negative 2 is what? The answer is positive 4. If you got that wrong, you might want to work on your multiplying skill in the skill building activities. The reason why it's 4 is because a negative times a negative is positive, and 2 times 2 is 4. So this is where things get tricky, because it says, what's the square root of 4 then? What number times itself is 4? Well, look, there's 2 answers, because 2 times 2 was 4, but so is negative 2. So because of this fact, anytime a negative times a negative, it's always a positive. So when you take the square root of a positive number, there are always 2 answers. There's always the positive and the negative answer every single time. Even though the calculator only shows you 1. Like in the calculator, if I did the square root of 16, it's going to only tell me 4, because 4 times 4 is 16. But negative 4 times negative 4 is also positive 16. So when you take square roots, there are always 2 answers, the positive and the negative one. So that's very important to remember, because it will always show up. However, that is not true when it comes to cube roots or fifth roots or other ones. It's only true if the exponent is even. Because right now, a negative times a negative, when there's only 2 there, it's positive. But like even looking at this example, if I add another negative in there, now it becomes negative. So there's only 2 answers when it's an even number, because once I add another negative, now there's 4 of them, 4 is even. Now it's a positive number. So what is 5 cubed? 5 cubed is 5 times 5 times 5, which if I put in a calculator, I'd get 125. Meaning, what is the cubed root of 125? Well, the answer to that is 5. Because what number times itself 3 times was 125? The answer was 5. All right, what about 2 to the power of 5? That means 2 times 2, which is at 4, times 2 again is at 8, times 2 again is at 16, times 2 for a 5th time is at 32. So then if they want to know what the 5th root, because there's a little 5 up here, the 5th root of 32 is, the answer is 2. Because the question is what number times itself 5 times was 32? Well, from this example over here, we saw that 2 times 2 times 2 times 2 times 2, a total of 5 times was 32. So when our whole goal of this is to simplify these radicals. So all of these are radicals because as long as there's any type of root in them, it's a radical. And when we simplify them, our goal is to make, change colors. Make the numbers smaller or more simple. Like the square root of 400, for example. If I say, so it's a square root, so what times itself twice is 400? I don't know. I don't know what number times itself twice is 400. So here's how I'm going to figure it out. I'm going to start breaking apart the number. So here's how it works. So I'm going to keep it in a square root, but I'm going to divide 400 by something and try to split it into 2 numbers. So if I were to take 400 and divide it by 1, it's still 400. So the next smallest number would be trying to divide it by 2. If I divide it by 2, I see that 200 divided by 2 is, or 400 divided by 2 is 200. So what that means is that 400 splits apart into 2 200s. And so you see that 2 times 200 is 400. So these are the same thing. 2 times 200 is the same thing as 400. So I'm just broke apart 400 into 2 times 200. Now here's the thing about 2. The number 2 cannot break apart any further. Here's why. It's a prime number. And what prime number means is it can't be divided by anything besides 1. Because if I divide 2 by 1, it's still 2. But there's nothing else that you can divide 2 by and get another whole number. It would be a decimal. So in my math tools, right here is the list of prime numbers. So a little bit down after the calculator. And these are all the numbers that cannot be broken apart anymore. So 2 is the first one. Then 3, you can't divide 3 by anything else and still get a whole number. Then 5, then 7, then 11, then 13, and so on and so forth. So these numbers are prime, meaning that there's nothing that you can times it by to get that number. Like the only thing that you can get 3 by is 3 times 1. That's it. The only thing you can get 5 by is 5 times 1. However, for example, 6 is not a prime number because 6 can be split. It can be divided by 2. And 2 times 3 would become 6. So this is not a prime number because it can split apart further. But 2 and 3 cannot split apart anymore. So I'm going to try, my first step is to try to divide every number under the square root bring it as far apart as I can to get only prime numbers under there. So 2 can't split anymore, but 200 can. 200 is not a prime number. If I look here, see 199 and then 211 is the next one. Like it skips 200. So 200 can divide by something. Let's figure out by what. So it will obviously divide by 1 because everything divides by 1 to get itself. Can it divide by 2? Yes, it can. It can split apart. 200 can split apart into 2 and 100. So now this still equals 400. If I have 2 times 2 times 100, it's still 400. So it's not like I'm changing my original number. It's still 400, but I'm breaking it apart even further. So this 200 breaks apart into 2 times 100. But I had to make sure I kept this first 2 there, because that's still a part of it. So now, this one, I can't split apart my 2 2's, but this 100 can split apart. It's not a prime number. So I'm going to delete that 100 and replace it with something else. Let's see, what can 100? Can 100 divide by 2? You're always going to want to check 2 first. Yep, it becomes 2 and 50. 100 can turn into 2 times 50. Can 50 break apart more? Can I do 50 divided by 2? Yep, I do that and I get 25. So 50 becomes 2 times 25. Can I divide 25 by 2? No, I get a decimal. And we don't want decimals in this. We only want whole numbers. So then I'm going to check my next prime number. So I tried dividing by 2. It didn't work. I'm going to try dividing by 3. If I do 25 divided by 3, nope, still a decimal. So my next prime number to try would be 5. Because if I could divide by 4, then I could also divide by 2, because 4 splits into 2 times 2. So that's why 4 is not a prime number, and I want to try 5 next. Can 25 divide by 5? Yes, it can, and it gets a perfect little 5, which means I can replace 25 with the fact that it is 5 times 5. So now, can 5 split apart anymore? No, because 5 is on the list of prime numbers. So now, this is broken apart. This is still 400, remember, because it's not like I'm changing the number at all. Because remember, our whole goal of this whole lesson is not that we're changing things, we're writing equivalent forms. Meaning at the end, I still want it to be the same thing as the square root of 400. So all these numbers, two times 2 times 2 times 2 times 5 times 5 is still 400. So I haven't changed it at all, I've just rewritten it to look different. So here's the thing about square roots. One way to think about it is what times itself is 400. Another way to think about it is if it's under the square root twice, it can come out of the square roots. Meaning this 2 times 2 right here, they can combine together into 1. And I'm just going to separate it out real fast so you can see them all separated. So here's a unique rule with square roots. As long as it's multiplying, I can split them apart. So I can do that square root and come out and times it to another square root that has the next 2 times 2. So here's 2 of them in one square root, the next 2 in another. And then I could put the next 2 in another. And I could write them in any order. Like if I wanted to put a 5 and a 2 together, I could have, but it serves me no purpose because here's why. Here's what happens with each little part. This 2 times 2 is 4, right? And the square root means it undoes it. So the square root of 4 becomes 2. And this square root of 2 times 2 also becomes 2 because it's 2 times 2 is 4 and the square root of 4 is just 2. So basically what you see is if it's under the square root twice, it comes out and there's no more square root. The square root went away because we took the square roots. Here, let me show you in here. If I took the square root of parentheses 2 times 2, the answer is just 2. Because once combined, 2 times 2 becomes 4, and the square root of 4 is 2. So anytime it's under the square root twice, it's like they can combine together and come out of the square root. So this 5 times 5, well, 5 times 5 is 25. Here, if I change this to 5. 5 times 5 is 25. And the square root of 25 goes back to 5. So then that one's a 5. Well, remember, these were all getting multiplied together. The only reason why I could even separate them like this is because when you multiply, it's okay to split them apart only when you're multiplying. If they were to be added together, this wouldn't work, but because it's always multiplying, it works. So now 2 times 5 is 20. It's telling me the answer is 20. So is it true? Is the square root of 400 20? Let's find out. Square root 400, it is 20, because 20 times 20 is 400. 20 times 20 is 400. So I know that was a kind of long example when the answer question is why can't I just put it in the calculator then? Well, here's why. What happens if I try to take the square root of 54, that next example? Oh, I get a decimal. And I don't like decimals because they go on forever and ever, and they're not precise because you eventually have to stop and round. And a lot of tests don't like decimals either. So they will often ask you to simplify your radical. So this is why this process matters. So I'm going to delete this stuff so that we can do the square root of 54. To do square root of 54, what am I going to start with trying to divide 54 by? We always start with 2. Can it divide into 2? Yep, it divides into 2 times 27. Okay. Now can 27 divide by 2? Nope, it's a decimal, so then I'm going to try 3. Yes, it divides by 3 and then it splits into 3 times 9. 27 splits into 3 times 9. Now 3 can't split apart anymore because it's one of our prime numbers. See? However, 9 can because it's not a prime number. Let's see, can 9 divide by 2? No, it cannot. It gets a decimal. Can 9 divide by 3? Yes, it can. It splits into 3 times 3. So I'm going to take that 9 and split that one into the fact that it's the same thing as 3 times 3. So now I've split 54 apart, and 2 times 3 times 3 times 3 is 54. Here, I'll prove it. 2 times 3 times 3 times 3 becomes 54. So it'll stay the same as long as you copy each part down. Like this 2 never went away. And then once this split into 3 and 9, that 3 never went away. And now this 9 became those 2 3s. So every part's still there. So they're equivalent expressions. This is still the same as this, which was still the same as this, which is still the same as this. I'm just rewriting it. So remember, if it's under there twice, it means that they can come together. Like, for example, there's 3 3s. So I'm going to take 2 of them, these 2 right here, and they're going to come together. And together, if they were under their own square root, 3 times 3 is 9. And the square root of that undoes it and just goes back to 3. Meaning that 3 is the answer to that little part. Now this 2 and this 3 has no one to go with. And so they are still under the square root because they don't have a partner to come out of the square root with. So that means that they have to go back together because they're staying under the square root together. And 2 times 3 is 6. So the answer to this one, 3 goes in front, and then on the inside is the square root of 6. What that means is the square root of 54 is the exact same thing as 3 root 6 when I've simplified the radical. So to check it in Desmos, the square root of 54, they say is the same, according to our math, is the same thing as 3 square root 6. Oh, look, it's the exact same decimal, 7.348, 7.348. So they are the same thing. This is just the more simplified version. So a couple more examples. So square root of 32, I'm going to go ahead and pause the video and give you a minute to figure out what the square root of 2 breaks into, what numbers. Go ahead and type your answer like parentheses, blank times blank times blank. So the square root of 32 is 2 times 2 times 2 times 2 times 2. So when broken apart, the square root of 32 becomes 5 2's. And remember, for each group of 2, because it's a square root, it'll come out in front of the square root as 1 2. Only one of them, though. So this group right here brings out one of the 2's. But then this group out here also brings out front one of the 2's. So I'm going to write parentheses 2, because when it comes out, it's getting multiplied, because they're getting multiplied in here. So now, since there are 4 2's inside, 2 came out outside. There's still 1 left in the square root. So now we combine the 2 on the outside. 2 times 2 becomes 4. And then you still have the square root of 2 after that. So if we went into Desmos, the theory is that the square root of 32 is the exact same thing as 4 square root 2. Look, it's the same decimal, 5.656 for both. They are the same thing. They were simplified correctly. Next. So over here, remember, if you have 2 radicals being multiplied together, you're entirely allowed to put them under 1 as 2 numbers being multiplied together. Kind of like we did up earlier, where I was able to take them out of 1 radical and separate them into 2 different ones. You can also combine them into 1. That only works if they're the same type of radical, though. Like these are both squareds. It wouldn't work if this was a squared or a square root and this was a cube root. Like they have to be the same type of root. I could multiply them together to get one whole big one. Or since my goal is to split them apart, I can just continue splitting them apart. I just have to do both numbers. So 20, if I were to divide 20 up, go ahead and do the 20 by yourself and tell me what happens when you break apart 20 as far as you can. So for 20, it'll turn into 2 times 2 times 5. And that's the furthest you can get them broken apart. And then how about for 12? For 12, it's 2 times 2 times 3. So this is as broken apart as those 2 numbers get. And now remember, because it's a square root, if it's under there twice, I can combine them and take them out of the square root. So what's the first number you see under there twice? 2. I see 2 under there twice right here, and later on right here. Is there any other number under the square root twice? No, there's not. So I can bring 2 of the 2's out. So here's 1, because there's 1 pair. And I can bring out another 2, because there's another pair. Quiet, Sadie. But under the square root, I still have the 5. Times the 3. So now to finish up my answer, I have to do this 2 times 2 and combine them to one number. That becomes 4. And then under the square roots, I have 5 times 3, which becomes 15. And so this is the most simplified version of this. So to check that in Desmos, if I had the square root of 20 times the square root of 12, the decimal is 15.49. And then according to my answer, that should be the same thing as 4 square root 15. which look it is, 15.49. So I know my answer is right. All right, so the next two make it a little bit harder because they're not squared roots. This one's a cubed root because there's a little 3 right here, versus these were all squared roots because there is no number right there, and we assume it to be the 2. This one's a cubed root. The cubed root of 1,200 or 1,029. So I'm going to just go ahead and try to start breaking it apart. Divide by 2? No. 3? Yes, 3 and 343. Okay, so I'm going to try to take 343 apart. 2? No. 3? Nope, the decimal. Nope. Not 5. 6. 7. 7 works. 7 times 49. So this 343 splits into 7 times 49. So now, can 7 split apart more? No, look, it's one of my prime numbers. So it actually does not split apart anymore. But 49 is not on this list. So I can split apart 49. Let's figure out how. Let's divide by 2. No. 3. No. 5. I skipped 4 because it's not a prime number. No. 6 isn't a prime number, so then I'll try 7. Yes, 49 is 7 times 7. So 49 can split into 7 times 7. So remember, this is not a square root, so the rules are different because it's a cubed root. How many times do you think it needs to be under a cubed root in order for me to circle it and bring it out front? For cubed root, remember the question is what times itself 3 times is that cubed root? So if it's under there 3 times, then it gets to come out with an answer of 7. However, I can't forget that there's still a little cubed root and it still has the number 3 under it. So the cubed root of 1,029, is 10.0957. And my simplified answer is 7 cubed root 3, which is also 10.0957. So my answer's right. All right, the next one's a 4th root, which means if it comes out under there 4 times, it gets to get taken out. And now we have letters. So the letters work in the exact same way. If there are 4 of them, they get to come out as 1. So let's start with breaking apart 243 as far as you can. What does 243 split into? All right, it splits in 5 threes. 3 times 3 times 3 times 3. So that's 243. If I were to break up x to the power of 6, what does that mean? How could I rewrite x to the power of 6? So it's x times x, 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 6 times. So that's 6 times. So y to the power of 9 means you have 9 y's being multiplied together. W to the power of 3 means I have 3 w's. Erase the work on the other one so it's not confusing. All right, so I have entirely split this apart. So now, because it's a 4th root, it means it needs to be under there 4 times in order for us to bring it out. So, how many 3's do I have? 1, 2, 3, 4. Here's one group of 4. So because of this one group of 4, my answer gets to pull out a 3 in front of the fourth root. But there's still a 3 in there, right? This one's still in there. Next, with my x's, here's 1, 2, 3, 4. So here's 4 of them. And then 1, 2. There's only 2 more after that. So 1x gets to come out because of the 4 in there. And then since these 4 came out as 1, what's left in here is 2 more x's. It's left under the fourth root. Now I'm going to look at my y's. Here's 1, 2, 3, 4 y's. And then 1, 2, 3, 4 more y's. And then there's 1 more left alone. So here's one group of y that gets to come out. Here's another group of y's that get to combine and come out. But then there's still 1 y left under the fourth root that didn't get to combine with anybody. And finally, we look at our w's. There's 1, 2, 3 w's. So there's not even 4 to come out, so they all have to stay under because of the fourth root. But when I combined these front 3 together and simplify it into one little thing, what is my answer? My answer for this first part is that it combines to 3x. The 3 doesn't change because there's no other number to combine with. The x doesn't change because there's no other x to combine with. But this y and y can combine together into y times y is y squared. Then we have the fourth root. Now under the fourth root, if I were to combine all of these together, what would my expression be? Under the fourth root, so the 3 has no one to combine with, so I can just write the 3. There's 2 x's being multiplied together, and x times x is x squared. The y is alone, so I'm just going to write y because there's only one of them. Then w times w times w is w cubed, or to the power of 3. So this right here is the simplified version of this radical up here. So I grabbed the answer and I pulled it down, or I pulled the original question down to where the answer was to show you, because with the letters, it'll take forever to type all of them out the way I did. So a quicker way would be, so with the x's, I have 6 of them, right? Well, if I need 4 in order to bring 1 out, so I'm minusing 4 away, then I'd be left with 2. So 2 is not a whole nother 4. So I know I pulled 1 away with these 4, so 1 came out. And then I was left with 2. So I left 2 in the exponent. With the y's, to do that quickly, I know I have 9. I take away 4 to bring out 1 of them. But that's still left with 5. So I can take out another 4. And then by taking out another 4, I'd be left with 1. So then my answer, here's one group of 4 that came out. Here's another. So y squared because 2 of them came out. And then there's still 1 more left under the root. So there's the 1. And then 3 isn't even a whole 4. So then I know there's still 3 under there. And that's a quicker way to do it without writing out all of the letters. So the language for this lesson is if-then statements. And we use these a lot in math. For example, I would say if 8 splits apart into 2 times 2 times 2, then the square root of 8 is 2 square root 2. So the whole gist of an if-then statement is that you start it with if this, so if something is true, then something else must be true. So looking back at our CLO for today, this is what I said you'd be doing. So go ahead and you're going to write me a statement in your own words, and you need to use if-then statements somewhere in your response. And you need to try to use as many vocabulary words as possible. And tell me in your own words what we did today in this lesson. So for my example on how to do this, here's how I'd write something like this. I'd start with trying to make up an if-then statement. So if, and what do I usually start with? I usually start with some radical when I'm doing this. So if I have a radical, then what if I have one? Well, what do I want to do? I can simplify it. Then how do I simplify it? So by, and this is going to explain how we do it. By splitting the number apart into an equivalence expression with only prime numbers being multiplied together. That's our goal in all of this. If we go back to the notes, our very first step on all of them was to break them apart into this prime number only situation. And then just to use another if-then statement, if I have only prime numbers under the roots, then I can combine however many that root calls for. So if it's a squared root, it calls for 2. If it's a cubed root, it calls for 3. And bring that number out front once. If I have done that for all numbers, then I can multiply the numbers on the outside together and the numbers on the inside together to get my final simplified radical expression. All right, so this is super intense because it has lots of big words, but it's basically all the steps of what we did. I used if-then statements every time. You don't have to always use if-then statements every time. If-then statements get boring. So you could have switched some of these up. As long as you used it once, it would have been a good response. I definitely use the word simplify a lot. I use the word radical right here. I use the word root right here. And then I realized I didn't use the word exponent. So one of the ways that I could go back and edit this is by saying, if I have letters being multiplied together, then I can combine them in the exponents. So as we continue to do these, hopefully you'll get better at summarizing the steps of everything we did, using all the vocabulary and talking about it in a very mathematical way.